Alrighty, it's wiring diagram time. Alrighty, it is time for the wiring diagram. We've done a few videos now on the bike generator, so I thought it was about time we showed you a wiring diagram. I'm going to do two actually, so I'm going to do a basic one, which is how the bike generator started, with basically just the generator, battery, alternator and some switches and fuses and that kind of thing. And then I'm going to show you the diagram of how the generator is now, which is quite a bit more complicated than when it started off. It's kind of evolved over the time. If you've not seen the videos, the other videos of the bike generator, we've got an overview, we've got a demonstration, we've got various bits of building circuits and talking about different ways to do it in a step-by-step instruction video. There's links in the description below. If you want to link what you see in the diagram to the generator itself, click those links, have a look, play about, find some good stuff on the channel. And if you like this kind of thing, please do consider supporting us, subscribe to the channel, all that good stuff. I won't blag you because everybody blags you about subscribing, but you know what to do if you like it. So let's get into it. Actually, quick disclaimer before we start. This diagram is what we've done to build our generator. I'm not making any guarantees as to whether it's safe or not. I've used the generator for a couple of years, it's been absolutely fine. But you might use different componentry with different tolerances and different types of things on there. So I can't guarantee that what you build will be safe. So what I would suggest is, if you don't understand about electronics and electrical stuff, get some advice on the componentry that you're going to use and put together to make sure it's going to be safe. You are dealing with stuff that could be quite dangerous in terms of the power that an alternator can generate, or a capacitor, a big capacitor or a battery. So do be careful. I'm not a qualified electrician. Although this is the Systemic Creative channel, building bike generators has nothing to do with our business. Do check out our business on the Systemic Creative website while you're at it. We do some great paradigm shifting organisational training and that kind of thing. This YouTube channel is just what we do to have fun, basically. So we're not qualified electricians. I'm giving you this diagram because it's what I've put together. Hopefully it's useful for you. But if you blow your kids up, it's not my fault. Alright, let's get stuck in. So we'll start with the basic diagram. This is how our generator began. This is how it all started, the first circuit that we put together. And this is nice and easy, straightforward. Anyone can build this circuit. Just a basic alternator, battery and load. And I'll come to what those mean as we go through. Got a few photos for you. As I said in the intro, if you do want to see some of this stuff in action, check out the other videos because we've got full step-by-step stuff that takes you through the generator. But I will tie this into some photos as we go through. So you can see we're starting off with an alternator over here. That's the main power generation device. Well, it's the only power generation device. The reason we've used an alternator is they're nice and simple, they're straightforward to wire up. Anything that's designed to run in a car will run with an alternator. So nice and easy. If you want a video about the pros and cons of using an alternator versus a DC generator, we've got a video on that. Check it out on the channel. Link below. So we've got an alternator there and we've got a 12 volt lead acid battery. Very important that it needs to be a lead acid battery for this circuit, because the way that this is wired up, this battery is in the circuit all the time when the generator is running, and lead acid batteries are designed to run in that way. If you're using something like a lithium polymer or another kind of battery, you need to look into a voltage regulation and charge regulation device similar to what you get on solar panels for charging the battery for a solar system. Lead acid battery keeps it nice and simple. Again, that's what's used in a car, and the reason is you can keep them charging. In the next diagram we're going to look at, we're actually going to switch the battery out of the circuit to prevent wear. because if you do keep them charging all the time at high voltage, it does wear them quickly. But to keep it simple here, this is the basic setup. So alternator here, 12 volt lead acid battery there. Let's start with the alternator and the connection. So we've got the main power output from the alternator. That's the big fat juicy cable that comes out of it. Usually pretty meaty off an alternator from a car. They put out up to 40 amps, sometimes 70 amps, so it can take a fair bit of power. So that's easily identifiable. And there are two other wires coming out of the alternator which are much smaller, much thinner wires. There's a voltage sensing wire and a field coil wire. So I've got the main power output, the voltage sensor and the field coil wire all into the same distribution block there. And we've got a master switch here. Now that's a double pole master switch. And what that does is it connects the battery into the distribution block. It connects the battery to the field coil and the alternator and the battery to the load. So that switch is doing multiple things, and it serves as kind of a safety cutout switch. If anything goes bad, you can press that and it disconnects everything from everything else basically. So that's a nice safety feature, and it means that when you switch that off, everything is disconnected. Nothing can be draining power, nothing can be taking it out of the battery. So it's useful to have that in there. Distribution block, that's just a connection block, you know, and I'll show you a couple of photos. Just a connection block which keeps everything together. Now for the alternator I use, this voltage sensor is required to be kept in the circuit, connected to the positive terminal at all times. So that's what it's done. Maybe on the alternator that you choose, that may not be the case. Some of them need to be wired to the battery and only sense on ignition, so they're just wired into the ignition circuit. And some of them don't actually have an external voltage sensing wire at all. It's all built into the alternator. So you need to check that on the alternator that you're using. It's usually in the instructions in the manual that comes with it. Then we've got the field coil. So if we were sort of doing this in order of operation, we'd switch this master switch on, and what that would do is connect the battery and the alternator into this distribution block and potentially connect the load down there. But nothing's going to happen at first because the alternator will only start generating power if you connect power to it to begin with. Once it starts generating power, it doesn't then need any input from the battery. So we've done this here with a switch. So this is effectively the ignition switch. So you'll start pedalling, and with an alternator it's important to start pedalling first and then start the ignition, and that's why we've got this switch, the master switch there, and a separate switch for the field coil. If you connect the power to the field coil immediately and then try to start pedalling, there's a lot of resistance because the alternator is generating power immediately. But because there is a sinusoidal variation in input through your feet, and I go into this in a bit more detail on the AC versus DC generator, it's actually very difficult to start pedaling at a consistent rate. You get a sinusoidal resistance and it starts getting very difficult to pedal. So it's important to start pedaling first and then have a separate switch to connect your alternator in. And it needs a resistor. It needs a resistor on there so that you don't get too much current going through the field coil. The value of that resistor will depend on the alternator that you use. So I've deliberately left the value off because it depends on the alternator you're using. On our circuit, I just use a little bulb, which is the same as the bulb which is in the dashboard for the car that it came out of. So older cars tended to just have a bulb, an ignition bulb, and when you turn the switch it lit up on the dashboard. Modern cars are a bit more sophisticated than that, obviously. But that works fine as a resistor for my alternator. Again, you just need to check what works for your alternator. So you can see there we've got the that's connected to the positive, the voltage sensor is connected to the positive, and the main power output is connected to the positive. Just to go back to basics, anything in red here is positive, anything in black is negative or ground. All the negative terminals are connected together and they're connected to the casing on the alternator. So in a car, that's how it works. The alternator is bracketed in there and that serves as the ground as the negative. Those can all be connected together. You see that comes off the load there, comes off the battery, comes into the alternator. The next thing we've got connected around the alternator is this voltmeter and ammeter. So this measures the voltage and the current, and depending on the one you've got set up, it'll measure the current through the distribution block, or it'll measure the current on the main output of the alternator, or on this there, which is the output to the load. Depends on where you put the sensor for the meter. The voltmeter will tell you the voltage from the distribution block versus the alternator or the battery. So if you just switch this master switch on before you start pedaling, it'll give you the voltage of the battery. Once you start pedaling and you activate the field coil, it will give you the voltage from the alternator, or the total voltage in the circuit, which will always be higher than the battery, because the alternator will usually generate between 14.2 to 14.4 volts depending on the alternator. It's important to have that in, because if anything goes wrong, it means you get to know about it, particularly voltage. You don't really need the current meter. I had it just because it was interesting to see how much current I was drawing off it. But you do really need a voltmeter on there, because it tells you if anything is wrong. Most alternators will have voltage regulation and rectification built in. Important to check that. The alternator I've used does have it built in. If yours doesn't, if you've got it off a motorbike or something like that, or a truck, and even some cars, they don't necessarily have it built in, so it's very important to check that. If you try and use one without rectification or voltage regulation, you're likely to cause severe damage to whatever you're trying to charge, at least, and or your battery. So you do need that circuit in there. Most car alternators tend to have it built in, so it's good to use that. What's part of what makes it easy using an alternator. So the voltmeter will tell you if that's working properly. So an alternator should always put out somewhere. If it's designed to charge a 12 volt lead acid battery, it should be putting out somewhere between 14.2 to 14.4 volts. You can get some that are a little bit above that. You can get some that are a little bit below that. But generally speaking, that's the sort of range that you're looking at. Again, some truck batteries, some motorbike batteries, they may be for a 20 volt circuit or a 24 volt circuit. So do double check what your alternator's designed to do. So that's the alternator area. 12 volt lead acid battery is just exactly what it says on the tin. It's just a 12 volt lead acid battery. You can use a sealed lead acid battery, a small one, or you can use a larger one that's intended for a car, a vented lead acid battery. I've got a 7 amp hour on my generator, because I don't need it to. I'm not using a lot of power from the battery, so a 7 amp hour is entirely sufficient. Car batteries tend to be 40 amp hours and above. You really don't need that on a bike generator. You can have that if you want, and what you could do is charge that up, and then you could draw lots of current and charge lots of things from it if you wanted to do it that way. But be aware that a large battery like that, a 40 amp hour, will draw a lot of current from the alternator when you connect it into the circuit, which may make it very difficult to pedal. So just be aware of that. A small one is probably better if you're a beginner and you're just setting this up to do some basic stuff. You've just got one load. A small battery is probably advisable. In fact, when I set this up, I just used a 4 amp hour. So the fuse there, you'll see there's a fuse there and a fuse here. So the fuse there is to protect the battery, and what this needs to be rated slightly under the maximum amp hour rating on your battery. So I've got a 7 amp hour at the minute, and I've got a 6 amp fuse on there. You could put a 7 amp fuse on there, that'd be alright, but I like to keep it safe, so I've put a 6 amp fuse on there. What that means is if you've got a load there, you connect something which suddenly it short circuits, or it tries to draw more current than the battery can supply, it protects the battery, so the fuse will blow. Make sure it's a quick blow fuse. The fuse will blow and the battery will be protected. That's just if there's something wrong with the alternator, or if you connect a high load, it becomes more difficult to pedal, and it may just be that you're not concentrating, or you don't apply the force quickly enough and it draws too much power from the battery. So that's important, get a fuse on there. This fuse here is to protect the wiring down to the load circuit, and also to protect whatever you're charging. So the load, for anyone who's a beginner to this kind of terminology, the load is just whatever you're connecting, the electrical item that you're connecting to the alternator to charge it up or to make it work or whatever. You might be connecting a phone, a laptop, something like that to charge it up, a power bank. You might want to run a basic appliance or something like that, a computer monitor, whatever. You might want to power a sound system, so an amplifier, speakers, that kind of thing. All of that is the load. And that sits here on there. Now on this circuit we've just got a single load and a single switch, and that says handlebar switch. The reason for that is you need the switch to control the load on the handlebar, because you can't be getting off the bike in order to switch the load into the circuit, because then you have to stop pedaling and you've got to restart the alternator. So you need this on the handlebar in order to make it work. And that's the whole circuit really. So the negatives all connected together, they go back into the alternator casing to create the circuit. So your circuit runs sort of like this through there. The reason the lead acid battery here, the reason that is connected into the circuit permanently, so this is a double pole switch, so it connects both the battery into the circuit and the load to the circuit at the same time. The reason for that is, with an alternator, even though it's got regulation and rectification built in, you still get a slightly lumpy signal. The kind of, if you look at the signal, you've got sort of 0 volts down there and you've got 14 up there. It does this because an alternator generates alternating current, which will go sort of like this. So the rectification cuts off anything down here, but you still have a slightly lumpy signal. So the battery there smooths out, does a little bit of smoothing for the circuit. So that protects your load a little bit. Now a capacitor is actually better at doing that than a battery, but a battery will do it to a degree. And we're keeping it simple, so there's no capacitor in this circuit. We're keeping it simple. So that's why we've got the battery switched in. Also, when you switch the load on, if it's quite a high load, due to the conservation of energy, and again, if you're new to this kind of thing, the more current you draw from your alternator as you're pedaling, the harder it is to pedal. So if you're charging a phone, you'll barely notice it because the power a phone takes to charge, unless you've got like a super quick charger, in which case you will feel it because they can draw up to 30 watts nowadays. If it's just like a 5 or a 10 watt draw on a phone, you barely feel that. But if you plug a laptop in and it's drawing 90 or 100 watts, you will feel that when you plug it in. And it may be that if it's quite high current, it could stop you pedaling because it can be quite surprising if it's a sudden switch on. So the battery just lets you ease up your power output through your legs, if you will. So it gives you that leeway as you switch the load on. So it just makes it all a bit easier if you leave that switched in. Just be aware of the load that you've got on there versus the amp hour rating of the battery. It is possible to switch the battery out of the circuit, as I mentioned earlier, and just have the alternator. So you could have two switches there, have this master switch, or get rid of this side of the switch altogether and just have a switch that switches the battery into the distribution block, and then you can switch it off. So you'll have the alternator connected directly to the load. The problem with doing that is the rectification circuit in the alternator, if you don't connect the load immediately, sometimes the voltage starts to climb because there's no load on it at all, and it starts to build up charge in that circuit, and that can damage the alternator, it can damage the circuitry, and at worst it can start melting things and causing serious problems. But if you connect the load immediately, that won't happen, but this load will be receiving that lumpy signal. So you need to make sure that whatever's connected to it has some kind of voltage smoothing circuit built in. Now another advantage of using this alternator type circuit is that many things that you get that plug in to a car power outlet will have some kind of smoothing in there. So if you're using like a USB charger or whatever that plugs into that, often they have smoothing circuits in, but do check it. Always check that, because you don't want to blow, you don't want to damage a really expensive phone or a laptop or something. You don't want to cause it a problem. And an altering voltage like that can cause problems to delicate electronics. If you're just powering light bulbs or like incandescent light bulbs, it's not a problem. It doesn't really matter. The filament might blow a little bit earlier than it would otherwise, but I wouldn't worry about it then. But certainly with microelectronics, you want it nice and smooth. You also need to make sure that the load on here will tolerate the voltage from the alternator. So a 12 volt lead acid battery, the standing charge should be somewhere between 12 and 12.8 volts for a fully charged battery. But an alternator, as I said, is going to put out over 14 volts. Stuff that's designed to work in a car circuit will be fine. Again, makes it easier because it will tolerate that, because it's designed to tolerate it. But if you're using something which requires a specific 12 volt load, you probably want a separate voltage regulation in there, which keeps it down to 12 volts. Otherwise, you might damage your load. So that's the basic circuit. That's what we're looking at. Let me show you a couple of the pictures. So you see there's the alternator, the battery there. Now the load switch isn't on, so this was even earlier than when I had the master switch on. So this only had a switch on the handlebar, but the master switch will go there, and you'll see it in the next photo. Here's the battery. That's just a 4 amp hour, as I mentioned. That's the socket coming off there for the load, and that's plugged in, and I've got it on an adapter there. Now you can see the bracket there. That's where I fitted the negative terminal from the battery to there. The negative from the load goes to the battery terminal, and then that goes onto the bracket, and that's connected to the casing of the alternator. Do make sure that when you bracket your alternator up, that's nice and clean for the connection. See up there a bit of a slightly bodged switch on the handlebar. This was the first iteration of the generator, so we'd literally just set it up there. So there's a handlebar switch for the load. And here you can see it's evolved a little bit. That's the master switch there. That's the voltmeter and the current meter. See volts on top, current at the bottom. There's the sensor. That's the sensor for the current meter. So in this case, it's sensing current which is coming out of the alternator. And you can clearly see there the field coil and the voltage sensing wire coming out of the alternator. Battery terminal from the top. Okay, so here we have the wiring diagram for the generator as it is now. It's a little bit more complicated, as you can see, but don't panic. The original circuit there is embedded in this more complicated circuit that we now have. It's just grown over time. We built it on that original circuit, and we've just added more bits to it in order to make it more flexible and so that we can do more with it. So one of the things that we needed from our generator was to use it as a training aid. So we needed to make it so that we had different degrees of resistance, so different loads that we could switch in and out as we wanted to increase the difficulty to pedal and thereby increase our training power output. So we've added 3 extra loads. There are 2 extra DC loads, as you can see there, and there's also an AC load. So I'll come back to that in a sec. So we've got DC load 1, DC load 2 and load 3, and they are separately switchable. And there's a master load switch then, and that takes the place of the big master switch that we had in the previous one. And as I mentioned, we can now switch the battery in and out separately. So I'll come back to that shortly. These loads, what they mean is we can switch one in and we can have sort of a basic amount of power on there, so it just gets us warmed up. And then when we want to pedal a bit harder, or if we want to switch charge more things or power more devices, we can switch loads 2 and 3 in as we want, and we can switch them in and out at multiple times. So as we said last time, whatever power you're taking out of the generator, you have to put in. So the more power you're drawing out, the harder it is to pedal. So you can have these set up to whatever you like. You can plug devices in there. You can have maybe a phone on this one, you could have a laptop on this one. You could put something like for a demonstration, you could put a blender on there. You could have an amplifier to power a music system, a TV screen, a projector, something like that. Well, projectors take more power than you think to power, so you need a small one. So that gives you some flexibility as to what you can do there, and you'll see that each of these are individually fused. The reason for that is it just protects the wiring, so you can have slightly different, you can set these differently for whatever you want on there. So if you wanted to put a maximum of say 2 amps on there, you could have a 2 amp fuse. If you wanted something bigger on there, you could have a bigger fuse. And then this fuse then is set to the maximum of all of your loads combined. So this will blow if there's a major problem or if everything's running, but these individual fuses are going to blow if there's an individual problem in one of these. So you see we've also got an AC load there, and we mentioned that an alternator actually generates current as alternating current. It has internal rectification which changes that to direct current or DC, and that's what comes out of here. And generally it's most efficient to then use devices powered from DC, because every time you change it from AC to DC or DC to AC, you lose some of the power. So alternators aren't very efficient. They don't need to be in a car. They're not designed for efficiency. Inverters are usually more efficient, but still not completely efficient. The one that we're using on our generator is about 90% efficient. So in other words, if you want 90 watts of power out of it, you've got to put 100 watts of power into it. So what this means is that you can change some of this DC current, if you want, back into AC and switch it up to 240 volts or whatever the voltage is in your country. We're recording this in the UK, we use 220 to 240 volts. And then you can just plug stuff in that has a standard plug on it. So we've got our inverter linked to a three splitter on an extension from the inverter, so we can plug 3 different devices in. I use it at the moment for my quick charge. I have a phone that has a quick charge charger, and it charges the phone in half an hour, but it needs 30 watts. So I can just plug that in, and on a half-hour session I can charge my phone completely if I use that. So anything that's got an AC plug on there you can use. So it makes the device even more flexible. You could of course exclusively have an inverter. You don't have to have any DC loads on there. You could just have an inverter and only power AC devices. And if actually you've got a bunch of devices with standard plugs on that you want to power using the generator, it makes sense to do that instead of buying new stuff to power it directly from the DC. You'll see there's a fuse on there. That just prevents any problems that are inside the inverter or anything that goes wrong with it. It's got a fuse on there which is appropriate for the size of inverter that you use. And there's a fuse there. In practice, this fuse is going to be in the plug of the device that you use. Most standard plugs for household sockets will have a fuse in them. So that fuse is going to be in there. I've put it on there just to demonstrate that it exists, basically. Now you can buy inverters. A quick note about inverters really. You can buy them with a whole huge range of different powers. The one that I've got on there is a 150 watt inverter. I don't envisage using anything more than 150 watts of AC power on the generator. You may want a bigger one than that because you may want to power more stuff. Have a think about that. Choose a power of inverter to suit your needs. What I would suggest is just think about how much power you're realistically going to be able to put out through your legs, because it certainly ain't going to be more than about 400 watts. And even 400 watts, unless you're a professional cyclist, you're not going to be able to put 400 watts out for any length of time. So for the vast majority of people and purposes, a 300 watt max inverter is all you're going to need. If you are Chris Froome, Tom Dumoulin, okay, maybe you want a bigger one, I don't know. But very few people are going to be able to put out more than 400 watts or even 300 watts for any significant amount of time. So do bear that in mind. There's no point buying a 1,000 watt inverter because you ain't going to be able to put out 1,000 watts. Okay, so that's the load side. You'll see we've also added an extra voltmeter up there. In fact, you don't need 2 voltmeters at all. The only reason I've added one rather than just replacing that, it was just easier than moving this one. This one's set up and it's a volt and current meter, as I mentioned on the basic diagram. This means I can also have one on the dashboard. So this is an extra voltmeter. So I've got voltage and current on the back, and I've got just voltage on the dashboard. So it gives me a bit of flexibility as to where I can look at stuff from. But it's good to be able to see that voltage, as I mentioned on the last diagram, just so you know if anything's going wrong. So the battery is now switchable out of the circuit. So what this means is we can power the alternator, we can set it going, and then we can switch the battery out of the circuit. As I mentioned last time, that leaves your loads a little bit vulnerable if the alternator is just powering them directly, because you get that lumpy DC signal. However, we've added a capacitor. Now the one we've added is a big old capacitor, big juicy thing, a farad, a full farad. It's a car audio capacitor. Now capacitors that size are fairly standard for car audio systems, but in the world of general electronic circuits, 1 farad is absolutely huge. You don't tend to use them that big in electrical circuits. But what this gives us, that big capacitor, it means that if we switch something on, particularly an inductive load, inductive loads tend to have a spike they draw a spike of power right at the beginning when you switch them on, and then they drop down to the steady state consumption. Whereas a resistive load will tend to just ramp up and it stays at its current. I'm not going to go into more details on that because that's a whole other video. But the capacitor allows for that spike without you feeling a sudden resistance in your legs as you're pedaling. So the power is drawn out of the capacitor, and a capacitor can discharge almost instantly. So it's much quicker than a battery. So it means that you can have a high current draw, a high momentary current draw, and the circuit will withstand it. Whereas you can damage a battery by trying to draw too much current too quickly. And if it goes into your legs, then you're hitting a wall of resistance effectively. So the capacitor means that it can satisfy those things. It will also smooth out the lumpy DC signal that comes out of the alternator. So it serves 2 purposes. Now you'll see we've got it's connected twice into the distribution block, and actually although here we've got it coming into the capacitor in 2 different places, actually this is just one connection. There's just one positive terminal on the capacitor. These are just connected together at the capacitor. The reason we've got 2 is quite simple. They're both switchable separately. A capacitor this size, a farad, will draw, as it can discharge current instantly, it can draw current instantly. And it will draw a lot of current very quickly. So if you switch it in without resistance, and again that's going to cause a problem. As you're pedaling, there's just going to be a sudden wall of resistance and it could stop you pedaling or whatever. So we've got one circuit, one wire there with a resistor on it, and the value of the resistor you need will depend on your capacitor, so you'll need to check that out as you're looking at the values you want to use. So what we're doing is we're pedaling, we get the alternator running, we get it charging, and then we switch the capacitor on with this resistor in line. And that means the capacitor charges up slowly at a manageable rate. Once it gets near to its full charge, we can then switch this connection on, which has no resistance on it. And then you can either leave that switched in or switch it off. It doesn't really matter. The current will tend to draw out of the one with least resistance in it. If once you switch a load on and it draws current, it'll tend to draw it through either or both. But what you don't want to do if you're using a big capacitor is leave the resistor in, because it kind of defeats the object of being able to handle that big current spike. So this is how we use it. It works really well, gives us that flexibility, and just means we can charge it up at a reasonable rate. You'll see also one little change. The eagle-eyed among you might notice this little change there. We've changed this from a push-to-make, push-to-brake switch into a momentary switch. It just makes sense to have a momentary switch for the ignition. Just means we don't accidentally leave it on. And you remember I mentioned that we used a little bulb as a resistor. That's handy because if you leave it on, the bulb lights up. But this means we can't leave it on. So we're never going to, if we leave the battery connected to the circuit, we're never going to leave it draining, by putting power into the field coil all the time. It just activates when we do it. This switch number in there, 1, 2, 3, 4, 5, 6, 7, 8, might look a bit strange because it kind of, doesn't look like it's labelled sensibly. The reason for that is they are labelled in order of the switch box that we have placed on the dashboard at the front of the bike. So that little momentary switch there, that's the ignition switch, switch 1, and then we've got 2, 3, 4, 5, 6, 7, 8 Ignore that 1, 2, 3 there. That's for the DC loads 1, 2 and 3. So I labelled it on there just to make it easy when I was doing it. I can see which order the switches come in. You can order them in any way you like, obviously whatever makes sense to you. And you'll see there is the voltmeter that's on the dashboard. So I've got that nice and visible for me there. A quick note on switches. I had these switches, switch boxes lying around. These are standard light switches with a 10 amp rating. Now, they rated 10 amps at 240 volts AC. That means that doesn't mean they can take 10 amps at 240 volts DC or even 24 volts DC. I'm using a car alternator and it's a 12 volt DC circuit. So there's a rule of thumb that says an AC switch you can use it for the same current rating on a DC circuit. If it's 240 volts AC, you can use it on a DC circuit of 12 volts. It's only a rule of thumb. It's not valid all the time. It's only a rule of thumb. So I'd be careful when you're setting switches up. I won't go into all the whys and wherefores, but for an alternating current, if you think about any given time period in that, there are moments at which that current is actually zero because it alternates on a sine wave, between positive, negative, and you've got it on a sine wave. The DC current is always at its maximum value. So the tolerance on an AC switch needs to be less than the tolerance on a DC switch. So the contacts are further away on the DC switch, and there's a more rapid isolation of the contact as the switch moves. So it means that current ratings for the same switch are much lower for a DC circuit. I talked to my brother about this and he had a really good suggestion. Gavin, he had a really good suggestion, which was if you're building this from scratch and you're buying the componentry, some good switches to buy will be caravan switches, because they're designed for 12 volt DC circuits, and that way you're not worrying about rules of thumb or anything like that. You're going to get the right switch for the right type of current, and the rating on there will be exactly what you can use it for. So keep that in mind. 10 amps is quite a lot to draw off a bike generator. If you're powering 10 amps worth of stuff at 12 volts DC, at the alternator voltage, that's only about 140 to 150 watts. But if you remember, you've got friction losses in the system, and the alternator isn't particularly efficient. So you're going to be well over 200 watts, maybe 250 watts of power output through your legs. So you're probably not going to go much over 10 amps really anyway. But do bear in mind, whatever switches you use need to be suitable for the current that's going through them. Very important, because you can get arcing across the contacts of the switch, which can obviously be dangerous, and it can weld the switch together and just ruin it basically as well. That's what the switch box looks like. Here's the new back end of the bike generator. You can see the capacitor is in place back there. We've got a slightly beefed up battery, the alternator, the master switch down there is now just the isolator switch, the isolating load switch. That's the rear voltmeter as was on there before. The inverter, you can see it just nestled underneath there. This is from above, obviously. That's some power packs. We just charge power packs up and then we can use them as we're travelling or whatever. And a bit of a close-up there of the capacitor. Now, if you're interested in installing this capacitor, I recommend one of the videos on the channel, which is how to install the bike generator. I think it's bike generator capacitor setup is the name of the video. You'll find it on there. We demonstrate testing the capacitor, getting it in the circuit and wiring it all together. It's a good video. Have a look at that. That'll give you some good sort of how-to instructions for the capacitor. And as I mentioned before, there is a step-by-step instruction that's from the basic thing all the way through to the completed generator as well. So there's switches, and here's a final image. That's Bex on the bike generator. This is before we installed the capacitor, so the little blank bit where the capacitor goes, but that gives you an idea of what it looks like kind of in use and on there. There's normally some loudspeakers that sit on there. For some reason they're not there, I don't know why, must have moved them. So you can see it in operation there, and you can see how it's used. We've got a little platform at the front, got a laptop on there so you can watch stuff as you're doing it. as you're pedaling, and you know, all that kind of thing. Use training videos and that sort of stuff. So there you go. They're the wiring diagrams. If you've got any questions, feel free to whack them in the comments. I'll be happy to answer them. I do want to reiterate what I said at the beginning, which is that I'm not a qualified electrician. It's not our business at Systemic Creative to build bike generators and that kind of thing. It's something totally different. So I can't guarantee that these circuits are safe in any way for the componentry that you use. And of course we can't be liable or take any responsibility for what you do. These are for illustrative purposes only. They are an example of what we've done with our generator. You do need to really understand what you're doing with the componentry. You need to understand electrical circuits, and if you don't, please consult somebody who does, who's qualified to give you that advice when you're building a circuit. It's really important. You know, this stuff can be dangerous if you get it wrong. That said, don't let that put you off. These are not difficult things to build. You know, this basic idea is going to work for lots of purposes. You need to ensure you understand the tolerances and that kind of thing, but all that information will come with, you know, you'll be able to find the manual for the alternator. You'll be able to find the values you need for the fuses just by thinking about what you're going to do. So don't be put off. These are good projects to do, and you know, pretty much anyone can do them. You know, not difficult. So good luck. I hope that works. If you want to download these diagrams, by the way, they are available on the Systemic Creative website. There is a link in the description below, so you can download them and have a little look around the Systemic Creative website when you're there. As I said, it's not our business. This isn't really what we do. We just do this for fun. The YouTube channel is all about us just having fun and making some projects, going on some bike rides and that kind of thing. So have a look around the business website while you're there. There's some great stuff on there. We do some fantastic training programs, training courses, which have got some great feedback. You can read all about that. And we do consultancy for businesses as well. So check that out while you're there. Hope you've enjoyed the video. Thanks for watching. As I said, if you feel we've earned it, give us a like, give us a subscribe, and hopefully we'll be bringing you more fun and useful content soon. Have a good one.